Hello students, welcome. So last class we have studied about cantilever and what is a cantilever. A cantilever is a rectangular, long, lengthy I mean block whose length is much larger than other dimensions. For example, a rectangular scale-like thing shown in the figure, a bar-like thing, its length is much larger than other dimensions, breadth, thickness, etc. So we call it a cantilever. Okay, and a cantilever is fixed at one end, and other end is applied with a weight. So when a weight is applied, what happens? Cantilever bends. A bend like what is shown in the figure. Okay, when it is bent, there is a displacement to one end. That vertical displacement that is called a depression. Okay, depression shown with the notation delta. So cantilever can be bent either by hanging some weight at the end of the cantilever, or a cantilever can bend by itself. Cantilever can bend by itself. Okay, this way there are two methods by which a cantilever can be bent. Okay, in one case you can apply a weight and the cantilever bend, so there is a depression. And in the second case, a cantilever can bend by its own weight, because it is heavy. So by its own weight, it can bend. If you fix one end of the cantilever and just suspend in free air, so there will be a displacement, just a vertical shift. The shift again we call as depression. So we can find the depression when a cantilever is bent by its own weight. Okay, we are going to study about the depression of a cantilever due to its own weight. The depression of a cantilever due to external weight we have studied in the previous class. Okay, so today we will talk about that. Cantilever bent by its own weight, or cantilever bent by uniform weight. So this is a topic contained in the syllabus, so we will discuss it. Okay, so we consider a cantilever like that. Initially it is horizontally lying. Initially let the weight of the cantilever be, say, W, capital W is the total weight of the cantilever. Okay, and the length L, capital small l, be the total length of the cantilever. Okay, length of the cantilever. So you can obviously find weight per unit length. Weight per unit length you will get by dividing the total weight of the cantilever with the length. So that will be in kilogram per meter or kilogram per centimeter. Okay, so that is the third step. And now you assume some point P on the cantilever at a distance x. So okay, the point of fixing is A and P is some arbitrary point on the cantilever. So the AP is the distance x. And of course from the figure you can see PB is L minus x. PB is L minus x. So you can assume that the bar AP is bending with the weight of the remaining. How you will find the remaining? You know weight per unit length is W by L. So weight of L minus x of the bar. So this is L minus x. Due to this length, what will be the weight? That will be simply W by L into L minus x, because W by L is the weight per unit length. Multiply this with L minus x, you get the total weight of this length. You can assume that this is bending due to this weight. Okay, and obviously you can see from the figure that weight W by L into L minus x. Then if this much of weight is acting at a distance L minus x by 2 from the point. Why do we take L minus x by 2? Because if you take the point closer to P, it is not contributing. Whereas if you take the point at B, it is contributing heavily for the bending. So average is taken, that's why we take L minus x by 2. Okay, which take into account the initial points as well as the end points. So the average is L minus x. Okay, so we can now write the bending moment. weight is W by L into L minus X multiplied by L minus X by 2. So you know moment is equal to force into distance. Force into distance. This is the force, okay, and this is the effective distance. This is the effective distance. Why don't we take L minus X? Because that is not effective. Effective is average. Okay, half of that. So we take it L minus X by 2. So moment is simply W by L into L minus X into L minus X by 2. Okay, this is called bending moment, and we very logically we explain how this expression is coming. Okay, and again, because there is L minus X and L minus X, you can simply multiply. So you get bending moment is equal to W by 2L into L minus X r square. Okay. Now again, we in the previous class we have studied that in general, any type of bar when it is bent, the bending moment is generated. Okay, restoring bending moment is generated inside the bar will be equal to y ig by y is the Young's modulus, I is the geometrical moment of inertia of the cross section of the bar, and r is the radius of curvature of the bend bar. Okay, because the bar is bending in the form of a circular arch, so obviously it's having a radius of curvature that is denoted with a capital. Okay, this expression we have derived in detail. So we can equate this is the external bending moment here, and this is the internal bending moment. Obviously, at equilibrium, internal and external bending moment should be equal. So we equate y ig by r is equal to W by 2L into L minus X r. Okay, this can be done, and obviously we can write this for rearrange the terms. You write it for 1 by r. Okay, r is the radius of curvature equals W by 2 y ig L into L minus X. And this is the inverse of radius of curvature, and we know radius of curvature is nothing but 1 upon d square y by dx square. We have discussed it, we have proved it. Okay, second order differential of the any point, curvature at any point, finding radius of curvature at any point, what we do, we'll first of all take dy by dx at that point. Again, we will take d square y by dx square at that point, and then you take the inverse of that. That will give you the curvature at any point on the curve. Okay, because it is like a curve, and it is bar is bent like a curve, it looks like a curve. So obviously it can be represented with some equation. Okay, so we have now the expression for radius of curvature. We can substitute this value. Okay, so when you substitute, what we get, we can remove 1 by r, and when you place it here, we get d square y by dx square equal to W by 2y ig L into L minus X r square. Okay, here all notations are being well explained earlier. And since this is a differential equation, we call it a differential equation of a bent beam. Okay, you know this. And in order to solve a differential equation, what we have to do, we have to integrate it with respect to x. So when you integrate this expression with respect to x, one of the degree will be reduced. Okay, so we will get a dy by dx. Okay, dy by dx will be there. Okay, and on the other side, these all are constants. W, y, I, G, L. We can take it outside, and inside we will have simply L minus X all square into dx. Okay, we have to integrate L minus X all square into dx. And keep in mind that this L is a constant, and obviously this can be also taken as a constant due to integration. So prior to that, we square the L minus X term. So when you square L minus X term, what we get is nothing but simply a minus b all square form. So we have L square x square minus 2lx dx. We are simply squaring it. We expanded it. Again, you can see now we can integrate one by one. We can have L square dx. We can have x square dx, and we have minus 2lx dx. We have to integrate each term separately. Keep in mind that integral x dx is equal to simply x square root
This is a formula, general expression we require in our course of time. So what we do, we first integrate L square dx, that will be giving L square x. Secondly, we have x square dx, that will be giving you simply x cube by 3. And finally, we have minus 2lx dx. 2l is a constant, you take it outside. We will be integrating simply x dx. So that is equal to x square by 2. So that x square by 2 is equal. Okay, that is also clear. And now we have a constant c1 here. This c1 has to be evaluated. This value has to be calculated. So for calculating the value of c1, what we can do, we apply initial condition. What will be the value of c1 at the beginning? So for finding beginning, what we do, we on the bar you take x is equal to 0 point, that is at the fixing point a. When x is equal to 0, obviously dy by dx will be equal to 0 because there is no curvature at the fixed point. So hence when you put here 0, here 0, 0, 0, you will get the c1 is equal to 0. So our c1 got removed, and now you have simply dy by dx equal to w by 2yicl into L square x plus x cube by 3 minus 2lx by 2. Okay. So again we have this is a differential equation. Once again you have to integrate it. So when you integrate once again, what happens? This dy by dx will become simply 1 because dx cancel and integral dy is 1. And on the right hand side we have again L square x dx, integrate L square x dx, and x cube by 3 dx, and minus 2lx square by 2 dx. So 2 can be cancelled. So and again you see L square is kept as constant, and x dx will be x square by 2. Similarly here 1 by 3 integral x cube dx, that will be giving you x raised to 4 by 4. And third term, 2 to cancel, L is taken outside, x square. When you integrate x square dx, so you get x cube. And it is an integration constant c2. So this c2 again, you can find that is simply 0. Okay, by applying the initial condition, you will find that c2 is 0. So we have now the expression for y. And this represents what is the value of y at different x points. Okay, so because bar is curved and it has different x value, what is the y value corresponding to different x. Okay, that is clear. And this can be summed up by taking a common factor in the denominator, that is 12, and numerator you can take it as 6 L square x square. First term, and second one simply x raised to 4, and third term minus lx cube by 2. A common denominator is taken as per the rule for adding fractional numbers, and you can add up now. When you add it, all denominators are common, and further you must take care that this is a general expression, and when x become L, what happens at this point, the expression y will become delta. We can apply this value. We put the x is equal to L here at the one, and y is equal to delta. So now you can easily add it. Or become L. So what happens? We have 6 L raised to 4 by 12 plus L raised to 4 by 12 minus 4 L raised to 4. Now simply you can add because this is 6 plus 1, 7 minus 4 is equal to 3. So 3 L raised to 4 by 12 you will be getting, and 3 and 12 can cancel, and when you rearrange you will be getting what is called delta is equal to W L cube by 8 by 8. So this is the final expression for the depression at the end of a cantilever when it is bent by its own weight, and not additional external weight is there when it is bent by its own weight. Okay, this is a derivation. W, what is W? Total weight of the cantilever. Keep in mind, the Previous derivation, W was the weight that is externally attached. Here it is the weight of the cantilever itself. Small n is the length of the cantilever, and y is the Young's modulus, and g is the geometrical moment of inertia. Okay, that depends on four different cross section. There is different value for different type of cross section. Okay, so with this derivation, we have made clear how the cantilever, when combined by its own weight, can be found in equation. Like this here, you make your own lecture note based on this video, and please study this. Wish you all the best. Thank you.